Hello. Have you ever wondered what would happen if your body was exposed to the vacuum of space? First off, a vacuum is a space in which there is no matter or in which the pressure is so low that any particles in space do not affect any processes being carried in there. This is the question I was pondering and decided to explore it further. I chose the subject because I have a deep passion to someday work for NASA and hope to help the space exploration learn more about our vast universe. I used a scientific method to do my research, construct a hypothesis, and test the experiment, and so on. My question falls under the category of physics and vacuum science. So yeah, and now we're going to move on to my hypothesis, which is going to be something important in this, which there will be 5 test subjects here. The water, the jello, the balloon, the Twinkie, and pretty much the zebra cake is the final one. It may sound weird, but each of them have an explanation for each and every one of them. Okay, so now we're going to explain all of them and what I think will happen to each and every one. The water is the room temperature. Is going to be room temperature because the temperature kind of affects how long it'll go, but that isn't what we're here for. I think it's going to boil because as molecules pushed on by gravity while in space, no atmospheric pressure is pressing against the molecules, allowing them to move fast and have the ability to boil. This represents your blood, saliva, etc., anything else that's liquid in your body. The next one is the jello. So I believe it will boil and expand because it is 95% water. That exact thing makes it expand because it is 95% water. And also the air in there too, it also makes it expand too. The water just makes it boil while the air makes it expand. This represents the eyeball because of its texture and what it does. The third one is the balloon, which is a very popular choice for this kind of science project. So what I think will happen is it'll probably expand because the molecules inside are not being pressurized by pressure, allowing them to move freely and expand like your lungs will. This represents your lungs because of its actions. Because, well, everything has their actions is pretty much going to be explained as it. The fourth one is a Twinkie, which I think the air inside the cream filling will expel and expand outwards of the Twinkie. But it will have the cream or liquid come to the outside and rupture. And what I think it will be best resulted as is the intestines, which actually will be part of your body because, well, it will get into the inside of your body, so that's why it's pretty much represented. The fifth one is going to be the classic zebra cake from earlier. You may think this is weird, but I have my explanations. I think the filling will expand and break on the chocolate on the outside covering, but that is the part I'm talking about. The part that I'm talking about is that the plastic covering will double in size, and that is what I think will happen to your skin. Everything was a think, though, and probably most likely to be correct. So yeah. So now I'm on to my procedure, which is going to be another part of our project. After doing extensive background research, we began to construct our vacuum chamber construct. With the help of my father, we used an air compressor, hoses, special fittings, inches of vacuum gauge, and an old pickle jar, and of course a vacuum to create what we needed to conduct our experiment. And the vacuum is pretty much this way and whatnot. The vacuum that we used would be classified as rough or low, which is equal to 1 atmospheric MBAR. Maybe you may not have heard of it. Well, most people have heard of it, but we couldn't find what it was equal to because, well, we couldn't find anything really right now. So yeah, I'll come up with some more info later on Facebook. So to explain what an MBAR is, maybe start a definition series. The flow type would be classified as viscous and is determined by the close interaction of molecules. I then placed each of the 5 test items into the vacuum chamber one at a time, so we didn't have all of them going crazy. We needed to check one at a time so you know what's going to happen to each individual one. Well, maybe I could go for a finale soon enough. So yeah, another video. So yeah, after I tested all 5 of them, it was a pretty crazy what happened. So with the items we had available to us, we were able to create a partial vacuum using what we had. But to ensure accurate data recording for the items, I conducted the experiment on at least 3 times. You can't test it once and expect accurate results, so you're going to have to test it 3 times perfectly. Well, maybe at least 3 times. If you need it, then just go 4 or 5. Maybe 10 if you're that crazy. So yeah, after collecting all pertinent data, I then began to analyze our results, thus coming to a conclusion, which is close to the final stage of our, science, forgot what it was. You know what? Never mind. Never mind. Okay. With the items we had available to us, we were able to create a partial vacuum, which is also going to be important to explain because, well, space is pretty much a perfect vacuum. And because it is a perfect vacuum, we were unable to recreate exact results. And it's actually kind of impossible for almost everyone on Earth to create a perfect vacuum because space is pretty much the only perfect vacuum out there, pretty much. So, but we were able to collect enough data to estimate what the actual results of what these 5 items will do in space. We were able to create exact results of what would happen. And now we're on to our analysis. Which, yeah. Oh yeah, the video, yeah. So right now, I'll give you a good amount of time so you can pause the video and pretty much get to the link below me right now, okay? So just pause the video and I should pretty much be staying still by now. And yeah, you should understand. Okay, so you got 3 seconds to pause the video. 3, 2, 1. Okay, and now that you got that, now I'm on to my analysis. I forget all I said a lot. Okay, utilizing air from an air compressor to run a vacuum pump, I was able to obtain a partial vacuum of 26 IOV. If you don't know what that means, it pretty much inches vacuum. And I actually never saw that before. I just thought IOV will be a shorter of it. So, because it's hard to remember, IOV inches vacuum is actually a lot easier if you think IOV. Well, I think UF should be released, and so it would be like IV, but that'd be a little short, don't you think? Yeah, okay, moving on. If you look at the graph right up here, you should see a little bit right here. Yeah, that's true. Okay, but now here's the real part we're talking about. If you look at the graph, you'll see my compiled data concerning the expansion of each tested item. And what I mean by expansion is how much it got bigger in size, and that's pretty much what it is. So as you see right here, each of them were used and put in the graph for a specific reason, and their numbers in a specific reason. So now, because of what is up here, I will explain why each of them had their 5 results. With the flexibility of the latex balloon rubber, which is number 1, first place, it was able to expand and stretch more than the other compressed items. Whereas the water simply vaporized into gas instead of expanding. Like, doesn't have an air or gas. Well, hydrogen, but it needs oxygen. Well, no, I don't know. Oh yeah, 2 hydrogen, 1 oxygen, but that doesn't exactly create air, does it? No. But it couldn't expand because of the materials and molecules it was made from. Okay. And that's why it isn't even in the graph. But you should be able to see water up here. I actually added 5 pictures, so it was pretty genius to do that. Compliment PowerPoint right now. Microsoft PowerPoint, really, it's really cool. Try it. Just try it for free. Get a Microsoft laptop, whatnot, and just go on. So now that we got that, we're going to move on to my analysis graphs, which will be another part of our presentation. We'll need graphs to explain the data and what happened. Well, this is actually representing the 3 states of it and why they had that. So yeah, And this is for the water, and it kind of like solid liquid gas and like air. So yeah. Now up here you should see pressure and temperature critical graph, which is pretty much what shows the critical point at which water will boil. Okay. This is the critical point. It shows when anything around here shows when it will be unable to calculate if it's either liquid or gaseous. Up here, above the graph, it has more pressure and temperature, so that there will be a critical point up here too. So it'll be hard to decide solid from liquid, which is also something important. And this may be weird, but it's actually kind of the same, but all three of them together, it'd be like a weird thing. Like it could be a solid, it could be a liquid, it could be a gas. It's impossible to guess, really. And this graph kind of represents the same, but for water only, really. And it shows how immediately after water boils, water vapor, now effectively at zero pressure, can cool very rapidly. Like, it just moves very quickly. So yeah, the numbers pretty much, these are just like Roman numerals, like the 7, and 10, and 11, hexagonal. Not just, you should, well, I didn't have enough to do that. So now I'm just going to move on to my next thing, which is going to be our, what's it again? Oh yeah, conclusions. Jumping to conclusions. Yeah, that was the art, that was really genius. Okay, so that's pretty much what it's going to be. So now that we have all of these up here, I'm going to read what it's going to be about. Or say what it's going to be about. You get the idea. After thoroughly testing each item multiple times, I'd say around 3 or more, yeah. Analyzing the data collected and then comparing them with previous tests, these are the conclusions I obtained. 1, 2, 3, 4, 5. I thought 5 would be a good amount. It's like 10. Yeah, we want to go slow, but for real scientists, we do a lot because we want to know what happens to every item and why it happens. But these are the 5, and that's why they're happening. So now, because of that, because of the conclusions I made, I was able to see what happens to each of the items when they're exposed to the vacuum of space. Vacuum, I said that data earlier, what the definition was. But if you need to know again, just go back to the video. And don't forget to save your spot, which should be very easy to remember, because this is a video, kind of like YouTube. So, let's just, okay. So now that we got the conclusions, we should explain why each of these had these results, which is going to be important too. Everything's important for a reason, The water is the first one we're going to see. What I said up there is that it'll boil in space, but the vacuum isn't strong enough to make that happen because it's a partial vacuum. Remember that? And here's some facts. Water needs pressure in order to be a liquid and is unable to maintain its form in a vacuum. Vacuum. So yeah, but really, it needs pressure. Really, it's crazy. But yeah, it needs pressure. A lot of pressure. Okay. So as the atmospheric pressure decreases, water boils at a lower temperature, which is going to be really cool. Thus creating water vapor. You know what water vapor is, right? A lot of people don't know that. But in case for you little kids out there, it's pretty much like water in gas form, pretty much. So that's pretty much simple. And now we got that. The next part about the facts is that I'll need to explain why this occurs too. Why does it occur? Because all liquids exert a certain vapor pressure. When vapor pressure reaches or exceeds the surrounding pressure from the atmosphere, water will boil. Really, it will boil in space. Why is this important to know when talking about bodies in space? Well, the adult human body actually averages up to 60% water. But I'd say from my feet down to my chest, around my chest, just low, around the top of my man here. But if there's this guy, go up here. So yeah, that's just all water. Water. Okay. Let's think about it. So now, this is why I chose to use water to represent what happened to not only the water within your organs and tissues, but also your cells. Yeah. Okay, I don't need to explain that on Facebook. It's a little inappropriate, but bear with me. Okay, in 1965, at the Johnson Flight Center in Texas, Texas fans, you gotta hear this. No, it's just saying, he's a cute guy. He's just my brother, okay? An astronaut had a leak in his spacesuit while within a vacuum chamber. Not space, a vacuum chamber. They're trying to see what happens. So yeah. And also within 15 seconds after he had a leak in his spacesuit, okay. 15 seconds after he had a leak in his spacesuit, he passed out. But that doesn't mean he died. That doesn't mean he's dead. That doesn't mean he's dead. He just lost consciousness. So, yeah, about that. After he recovered, he's really lucky. After he recovered, he stated the last thing he remembered was that he felt his tongue beginning to boil. Okay. His tongue actually began to boil. It felt boiling water inside your mouth. That's actually so big. Let's move on. So with my test item 1 showing a slow boil and condensation forming on the sides of the jar, I feel that my hypothesis was actually confirmed. So yeah. So now the second one I'm going to explain is my balloon. My good old balloon. Those are rare to some people, but once in a while. But you want a balloon right now, right? Balloon pizza? Yeah, let's go on, okay? When the atmospheric pressure is the same on the outside of an object, pretty much, I feel that my hypothesis for the last one, When the atmospheric pressure is the same on the outside of an object, here, it is said to be in equilibrium when it's on the inside of an object too. That means they're pushing against each other, keeping it in form. Like, it's kind of like toe, but pushing more. Kind of pushing, like equilibrium. Like, imagine this side having the pushing on the outside, this one on the inside. They're pushing against each other. So that's pretty much what's happening. But think about this. When the vacuum chamber you saw it from the link below, okay, so here's what happened. You don't know why that happened? It's because of this. This side, the inside part of it, and the outside part of it had a big malfunction in it. The inside part of it actually had all the air sucked away from it, so there's no pressure on it. While this one still has the pressure from the outside pushing against it. I meant outside of the balloon, inside of the balloon. Yeah, sorry. Outside, let go. Outside, let go, because all the outside of the balloon was being sucked up. While the inside of the balloon, right here, was actually still in good form. But that means that it's unbalanced, not in equilibrium. So that actually put the inside of the balloon actually pushed on the outside because there was no force trying to keep it safe. So it was expanded and expanded and expanded. Pretty much expanding. Soon explode, pretty much. It's just like balloons blowing up in air. Heck, I'm not even close to it. So now when a partially inflated balloon tied off, we are able to obtain this. However, as you decrease the air pressure from around the balloon, the pressure remains the same is stronger than the outside pressure, thus creating the expansion. That's another way to put it. Now, this is representative of your lungs in space. If you try to hold your breath, yeah, like hold your breath. That's usually what would happen on Earth. But as that would happen in space, it would have a completely different result. There it is. Okay, when this is representative of your lungs in space, because, well, it's not gonna bear. I was just representing that again in case for any of you who had to go do something. Let me just pause the video again. Yeah, you can. Okay. Okay, that's enough messing around. And now that I'm trying to represent it, one thing you may want to think about is that if you find you lost in space, exhale as quickly as you can. But I'm just going to actually not think about it much, but because no matter what, you're going to die because you pretty much barely have anything to breathe. You'll just have to see how long you can survive. If you can't see anything all around you, you're dead. There's no way anyone can reach you. Unless there's an alien that just comes by and sucks you up. Okay, so now that I have that, I'll need to explain the next part of it. But, first off, if you have to find your lost in space, exhale. That's the final part. But if you can't see it, just die. Okay? Just kidding. Okay? With my test, I'm too expanding like I thought it would. Stop expanding. Okay. Now with it expanding, I felt like my hypothesis was confirmed because my hypothesis had the same idea as the conclusion, and yeah, pretty much it. So now we're on to my third option. This may feel like forever, but it will get over it. The third one is obviously my Jello. The other two will be a little shorter because it'll be really easy to explain. But yeah, I actually really want to use this like the Jello right now. Really, if you want to know, it's actually strawberry. Just very quickly, and it's strawberry Jello. In case you thought in the video it was cherry, I was wrong. It was strawberry. But it tastes like cherry. It really does. Okay, that's enough. So now the next part of it is the Jello, and now I'm going to explain why this result happened to it. And also, it may seem really weird, but how it boiled, but remember, it's 95% water, eh? Yeah. With Jello expanding and containing approximately 95% water, but expanding very little though, I use this to represent the human eyeball because that's what would happen to the eyeball in space after I did some research after I thought my hypothesis, so I knew what would happen right now. Okay, well that will actually have a different result in space. Think about that. Burp in space. That'd be cool, actually. If only we could figure it out. Okay, we'll get onto that in a different episode. Well, video. Episode sounds good, don't you? Yeah, let's move on. Okay, so now that we have that, it felt like with my test 3, I'm showing signs of boiling by the appearance of bubbles inside the Jello, and it's slightly expanding. Plus, I did some research, so now I know that's actually true. I feel that's my hypothesis. You may think I'm actually cheating on this, but no, I'm not. I actually didn't know. Like, I was just doing some research. You know, you gotta do research before you can do it, and actually, I'm really good at containing hypotheses after you do some research. Okay. And now, for my fourth one, which is gonna be the Twinkie. Bet you're wanting one right now. Come and get it. Okay. Sit up. Sit up. Okay. The real result in the Twinkie was actually the bottom because it was the weakest. You know, That's why we put it on the bottom side, you know. Plus, there's a lot of weak spots in there, so that's why. Really want to eat it right now. So now I'm gonna explain what happened to my Twinkie. So, unlike the balloon, the Twinkies are not elastic and are simply filled with air inside the cream and the cake. Don't forget the cake, but mostly cream, okay? So now, with the inner filling being whipped cream, it had more pressure than the surrounding Twinkie and expelled into the chamber. This is representative of your intestines. There, and the contents of your intestines will be expelled. And here's your, if you had clean underwear, you won't have any now. I'm gonna look freaky, but just forget about it, okay? Freaky eyes. Like my blue eyes? You better like my blue eyes. You're gonna like my blue eyes, okay. Okay, so now that we have that ready, that is pretty much what's gonna happen, pretty much. Trust me, I did research. I have more research. I'm gonna explain more of it later in this video. So yeah, just, you may think I'm slacking off on this part, but okay. So now I felt like my hypothesis was confirmed due to the research of the Twinkie. Want me to eat 16 at once? Okay. Really, I choke on that. Okay. That wouldn't be interesting though. Okay, fifth item. The zebra cake. It actually looks really good. I don't remember the place it was from. Like it was, you know, I'll just explain the series. Never mind. I'll just explain where I got it from later, okay? Just maybe search up zebra cake on Amazon or whatever you use, or maybe use your Paybucks or whatever. Okay, so zebra cake. That's going to be the next part. The use of the zebra cake acted a lot like the Twinkie, thus proving my hypothesis. I'm not done. No. The skin was represented as the wrapper. The skin was represented as the wrapper, not the zebra cake, the wrapper. I had to keep the zebra cake in here. In order to get it out, I had to undo the wrapper, which would completely ruin the whole thing. So, I just said zebra cake. Or, could have said zebra cake. Wrapper! Okay, it's the wrapper, okay? The wrapper was the one with the results. It's kind of like the skin. It's elastic. And now, more info. When the wrapped zebra cake was put in the vacuum chamber, it expanded to twice its original size, much like our skin would do in space, which, really, that would happen. I did some further research, so, yeah. Okay. Okay, that's enough. I'm starting to get a little tired. Okay, you may think it's a little late at night watching this, or maybe in the morning, I don't know. Okay? Get okay, let's go. Okay, as the water within our bodies turns to gas, it takes up more room and is pushing outwards due to an imbalance of pressure, and thus expanding your skin. And because of that, it expanded to twice our original size, much like our skin would do in space. So you'd be a fat blob. Fat blob. Okay. So pretty much because of the results and the research I did on this exact Twinkie. Wait, no, not Twinkie. Zebra cake. I felt like my hypothesis was confirmed because I looked through and that's what would happen. And Google was a little too lazy on adding that info to it. Maybe I didn't word it correctly. What? I'm a spelling champion. Okay, that's enough. So now that we got that done, let's go on. So now, as exposed liquid on your body will begin to vaporize, so the surfaces of your tongue and eyes will begin to boil. Without air in your lungs, your blood stops sending oxygen to your brain, and you will pass out in about 15 seconds. Because you don't know what you do, like, What's going on with me? Yeah. Okay. If you hold your breath, your lungs will continue to expand and eventually rupture because there's air inside your lungs. That's why I need to expand as much as you can before. And so if there's even one molecule in there, you'll die. Exhale. Exhale. Is that a word? Yeah. Can I have some static? That's enough. Okay, so now that we got that, if you hold your breath, your lungs will continue to expand, eventually rupture. What it means by rupture is kind of like it explode and start getting old or what. Just explode, you know? Explode? Yeah. Maybe we could do 16 Twinkies. Trust me, somebody's done a video on 16 Twinkies in a vacuum chamber. Check her out. Yeah. I'll add a link below that, right below the link. So if you want to click the wrong link, that's what I'm talking about, okay? So now that we got more of that info, I have more info. And more info. Okay. So, oxygen in the rest of your body will also expand, and that's the fact. Okay? You will balloon up to twice your normal size, but you won't explode. It's because your skin is elastic enough to hold you together. After 90 seconds of exposure, you will die from asphyxiation. If you never heard that word, it means you'll suffocate, okay? It means you'll suffocate. For all the babies, start learning. No worry, just learn at your own pace. Just watch this when you know about it, okay? So now, since the void of space is negative 454.81 Fahrenheit, I could barely remember that. Like, what was the number again? Then just came, you know? Okay. You will actually eventually freeze solid. Okay, freeze solid. You get it. You get the idea. Thermal conduction keeps you from freezing immediately. Thermal conduction. You know what that is? Yeah, I'll explain it. In order for your body to lose heat, it has to have something to transfer it to. It needs to lose heat. You may think that's weird, but really, it needs to lose heat. It needs to transfer it to something. And to have something to transfer it. And since there's nothing in space, not even air, you'll actually stay warmer longer. You won't freeze. I don't know why, but it's weird how your body would transfer heat just to freeze solid. It has its reasons. Okay. So now, it's pretty simple what's gonna happen after that. We're gonna explain our references. Yeah. Also, because I'm in the house, actually, I'm not available to this, so that's why I said watch the video. So it's not like I'm trying to think. Okay, it's hard to do. I have to find something. It's out in the garage. Or is it over there? Oh, okay. The references is going to be something else that I'll need to explain. It's not really important, but it shows where you got your information. Which pretty much where you get to get your teachers from. And if you look at that, then you're pretty much dead. Okay, so I have 5 references. So the first one is the USCS Physics Demonstration Room. Education Department Expansion in a Vacuum. Search it up. Second one is my dad, Damon Clemens. Yeah, just should have said the name. Never mind. Okay. The third one is the vacuumscienceworld.com, portal of expertise for vacuum technology. Number 4, NASA. Yeah, I said it like Sega. NASA, Sega. What's the difference? There's a huge difference. One is a video game series, and the other is space. Fifth one is 10.4, phase diagrams from Chemistry by Rice University, Chapter 10. Oh, and if you see your little series up here, thank you for helping me by giving me the info I need. And now that's pretty much the end of it so far. So now that I have that done, if you have any questions, just type them below and I'll explain to you through comment. Maybe through secret comment or something. Okay? I'll just explain through comment, okay? So now if you have any questions, just do. So thanks for watching my presentation and I'll see you next time. Goodbye.